cell level, the tissue level, the organ level. And we're just going to learn about basic approaches in terms of inflammation and repair, wound healing. Let us begin with some simple definitions. We all use the word inflammation. We use that all the time, but what exactly is inflammation? And inflammation, very importantly, is a response to infection and damage, but it's a response of vascularized tissues. And so only tissues that are vascularized can have an inflammatory response. Can somebody name a tissue that's not vascularized? Try the tissue that you can spend your whole life making a career out of. Yeah, so part of the teeth is vascularized. What part of the tooth? Have we gotten that far? So the pulp is vascularized, and when a cavity gets to the pulp, then what happens? It hurts.
It's not vital.
But if tissue damage is restricted to enamel or enamel and dentin, is it painful? No. You go to the dentist and surprise, you have a cavity. Somebody tells you have a cavity. So enamel and dentin are not vascularized tissues. So they are not capable of eliciting an inflammatory response in the presence of infection. You guys deal with infections all the day, all the time. That's actually what you will be doing. Cavities are infections. They're infections of hard substances, enamel and dentin. So it's kind of interesting. That's why caries are painless, because enamel and dentin are not vascularized tissue. And then when the infection gets to vascularized tissue, when it gets to pulp, bam, it hurts. And then somebody needs a root canal. Circulation is critical for inflammation because it brings all kinds of cells and molecules that we will learn about to the site that has been infected or damaged. And the purpose of all of this is to eliminate the offending agent. Inflammation is a protective response, and it's very, very important for survival. Without inflammation, you cannot get rid of the cause of an injury or the consequences of an injury. A couple of other basic points. A lot of mediators of defense, and by mediators of defense I'm referring to leukocytes. What are leukocytes?
White blood cells.
White blood cells. Can we name some white blood cells?
Neutrophils, basophils,
Neutrophils, macrophages, lymphocytes. So good, so good. Leukocytes are mediators of defense. We'll learn about different leukocytes and what they do. Antibodies. What's another word for antibody? Depending on who gives the lecture. I'm sorry? Hemoglobin? Immunoglobulins, yeah, immunoglobulins. So antibodies, immunoglobulins, sometimes one person uses one word, sometimes another. Just depends on the preference of the lecturer. And then complement proteins. We will go over the complement system. I'm sure that you all have gone over it in some form and fashion. So all of these things normally circulate in the blood, and they're recruited from the circulation to the site of the offending agent, wherever that may be. And they do a whole lot of things to damage the tissue in a controlled fashion that then terminates. So we'll dive in a little bit, begin with some basics and some concepts about inflammation. And then from time to time we'll really go in deep with the magic school bus and just flesh out some details. So some fundamental properties of what we'll begin with. And there are a couple of major players. This should be mostly common sense. You need blood vessels in order to deliver stuff to the site that has been injured, and you need stuff to be delivered. And stuff that can be delivered are first and foremost leukocytes. And you all have listed these, and you all are capable of listing these. We won't talk about them. Images like this, I'm not really going to talk through, and I'm not going to find a little line in the image and make that a test question just in terms of how I approach evaluating you all, but certainly any given image that's in a lecture, if you are able to look at that image and understand it from bottom to top, you have a really good grasp of what I'm trying to teach you all. So there are some major players when it comes to inflammation. A couple of other big picture facts we'll talk about is that inflammation rarely occurs without local tissue damage. So inflammation that is designed to, in some way, ameliorate or get rid of a problem, it usually comes at some kind of cost of tissue injury that would not have otherwise occurred. Certain disease states can be characterized by a really prominent inflammatory reaction that is best described perhaps as misdirected. So something like an autoimmune disease. This is the autoimmune disease doing what it was designed to do, but it's totally got one step wrong. And so instead of attacking something that it's supposed to attack, it's attacking, for example, one's skin. And then one's skin is blistering off of one's body. Or allergies. The cells that are important in allergic reactions are normal cells that do helpful things in us. But one can get, for example, hives or urticaria. You can get all of this tissue swelling and some amount of tissue damage. Frequently, it is the inflammatory response to an agent that is as much, if not more, a proportion of the clinical presentation than simply the infectious agent itself. So some teeny tiny virus like HIV can cause all sorts of problems, for example. Inflammation, in terms of big pictures, it can be local or systemic. We are, by and large, going to talk about local inflammation today, and in general in our lectures. There are a variety of systemic inflammatory responses that can cause widespread pathologic abnormalities. We will learn in due course about some things like septicemia, DIC, shock, so on and so forth. But generally, we're going to be talking about inflammation in terms of it being a local response to tissue infection or tissue damage. Local inflammation can have some systemic manifestations. Think fever if you're sick. Inflammation is designed to terminate when it has done what it is supposed to do. And then after it's done what it's supposed to do, tissue repair initiates. We'll spend the last little portion of our lecture today talking about tissue repair. Termination of inflammation occurs when the offending agent is successfully eliminated, and that sets into motion this process of tissue repair that is one of two things. It's either regeneration of surviving cells, in which case no scarring occurs, or there is scarring, and we all know scar from Lion King. But we will, in a formal sense, we will define scarring, what it is, and what its function is. Because scarring is different from regeneration. We would all prefer regeneration to occur, but why does regeneration not always occur? Why does scarring sometimes occur? Another big picture thing that you all have perhaps come across in one lecture or another are your cardinal signs of inflammation, your 5 cardinal signs. And depending on whether you like to speak in Latin or in English to one another, I put down the 5 in Latin and in English. I prefer English. Again, there are several causes for inflammation. In a slide like this, perhaps there are a lot of words on it, but if you sat down with a blank piece of paper and if you just took a moment, you could perhaps conceptually write out or think of some of these categories. And so there are a variety of categories that can result in inflammation. Certainly infections of all sorts of shapes and sizes and flavors. Tissue necrosis can occur from something like physical trauma, thermal injury like a pizza burn on the roof of your mouth. Ischemia can also result in tissue necrosis. We defined last time ischemia and hypoxia. Those are very important words to know inside and out. Certainly, foreign stuff can come into the body and cause all sorts of problems. And then there's problems with the immune system. Autoimmune disease, allergy. These are some pictures on the right here. This is a boy with measles, and this is somebody with scarlet fever. Measles is a viral infection, scarlet fever is a bacterial infection. We'll learn about these in due time, and you all will also learn about them probably in your virology or microbiology courses. And so certainly don't worry about annotating these two images and trying to figure out the differences between, and there's plenty of time for that. So we'll start to sort of, crack the door open into the nuts and bolts of inflammation and the inflammatory response, we'll begin with the question of how are offending agents recognized. And offending agents is somewhat of a big category. It can refer to microbes, it can refer to damaged cells, necrotic tissue. How is all of that stuff recognized? And so here in the top left is our cell, and we remember that the cell has all sorts of structural and functional components. One thing that's not illustrated here, but at least the cell membrane is illustrated here, is the fact that there are cellular receptors for microbes, and lots of cells have this stuff. Some cells are specialized at identifying receptors, but most cells do have at least some receptors. And receptors for microbes are on several membranes. They can be on the plasma membrane, and that's for extracellular microbes. They can be on endosomes. So if something's been ingested, and then once it's been ingested, it's been detected as foreign or noxious, then it can fuse with an endosome, so it can be discarded. And then floating around in the cytosol are also a variety of cellular receptors. So again, if you were to design a cell and come up with ideas of where it might be a good idea to place receptors, again, you could perhaps think of these three locations. So there's not too much to sort of memorize here. We can think through this a little bit. I do not know why I put this Star Wars image here. I don't exactly know how that fits in with the concept, but I guess this is a cell and these are microbes. I'm not sure.
The tractor beam is the receptor.
I'm sorry?
As they come in, that's how they receptor.
I suppose, but these are the good guys. That's the problem.
Not
And
the
like
Death
this-
Star. They're the
no.
bad guys to the Death Star.
Well, I suppose, but we don't want to be the Death Star. But I like that. That's the best explanation I
I
have.
think
here.
more appropriate for antibodies, probably.
What would be more appropriate?
That for antibodies.
For antibodies, okay.
Yes.
I'll make the change.
I don't
next year.
know.
That's smart.
So how are problems detected so that an inflammatory response can commence? So we've talked about receptors for microbes, whether they're extracellular or intracellular. There are also sensors, and I suppose that could be with an S, there are also sensors of cell damage. And conceptually, we learned about that a little bit last time we spoke in this course, when we talked about triggers of apoptosis, the role of the mitochondria, whether the mitochondria is intrinsically damaged, or whether the mitochondria initiates a programmed cell death. So there are sensors of cell damage, and these can recognize all sorts of problems in the cell, as well as molecules that are liberated or altered, like perhaps cytochrome C, if you remember that from the first lecture. Offending agents can also be recognized by the complement system. Complement system comprises 20 or so proteins that are circulating in the blood. We'll spend a few minutes on that later on. Also, white blood cells, a lot of them express receptors for antibodies or complement proteins that have opsonized microbes. So antibodies are also kind of doing their thing and catching stuff. And the tail of the antibody can be recognized by a white blood cell, by an inflammatory cell, shall we say, and it can bind the antibody and then begin to do its thing. Complement proteins do this thing that's called opsonizing or coating microbes, and so here are like these two polar bears that are opsonizing one another. We will define opsonization a little bit more formally in a couple of slides. Inflammation, you will have perhaps heard these terms. Inflammation can be acute or chronic. So because this is boring, I condensed all of this into one slide, even though there are a lot of words on this slide as a result. But inflammation can be acute or chronic, and if we formally define these two things, we'll sort of point out a couple things that are worth knowing. Acute inflammation certainly is an initial and a very rapid response to infection or tissue damage. This is what happens within a couple of minutes or at most an hour or so of falling off of your bike and, scabbing your knee. Acute inflammation subsides when the offending agent is cleared. Acute inflammation's job is to solve the problem. And acute inflammation can last for up to a few days. Chronic inflammation only occurs if acute inflammation cannot clear the offending agent. So that's what chronic inflammation is. Chronic inflammation is not required. It frequently happens, almost always, shall I say, but it's not required. Acute inflammation is characterized by exudation of fluid, and we'll remind ourselves of some words, transidate, exudate, and pus in the next slide, I think, and emigration of white blood cells, particularly neutrophils. So neutrophils are the main player for acute inflammation. In chronic inflammation, the main player is the macrophage. Macrophages work closely with lymphocytes, particularly T lymphocytes, but macrophages are the main player in chronic inflammation, and we will get back to that. Chronic inflammation is associated with more tissue destruction and healing by deposition of connective tissue, which is a little bit of a reference of scarring, the type of healing that occurs when there is a robust amount of tissue destruction. So let's spend probably most of the first hour talking about acute inflammation and getting into this process a little bit, diving into the details. There are a few major components of acute inflammation thinking conceptually. A lot of these make sense. So if you approach this from a conceptual standpoint, I think it'll all be rather nice and elegant. For starters, small blood vessels dilate, and this makes sense. It leads to increase of blood flow. It leads to slowing down of blood flow so that stuff that's in the blood can exit the bloodstream. And this also accounts for some of the clinical features. You know, we have our 5 cardinal signs of inflammation. Perhaps redness and warmth can be explained by this. The vessels, in addition to changing in such a way so that blood flow slows down and so that there's increased delivery of blood flow, the vessels also become permeable. This should make sense. This allows for exiting of various proteins that are present in the plasma, which is, shall we say, the fluid of the blood, and also cells, white blood cells, leave the circulation to go where they need to go. And then there's this process of going where they need to go. And then they go to where they need to go, they accumulate there, and then they do what they need to do. So that's acute inflammation, shall we say, in a nutshell. And we will explain some of these details a little bit more thoroughly next. We used the word exudation a minute ago. Exudation, formally defined, is pretty simple. It refers to the escape of fluid and other stuff, proteins and blood cells, from the vascular system, which is typically a sort of a tight compartment of its own, into interstitial tissues or perhaps body cavities. Today we'll talk about interstitial tissues. You know, you close the door on your finger and then inflammation begins in your finger. Exudation can take a few different forms. There's transidate, exudate, and pus. Let's just begin with pus, even though that's something of an exception. That's pretty easy. Pus is exudate that's rich in neutrophils. Neutrophils make things yellow. That's why an abscess is yellow. If you pop your acne zit, creamy yellow stuff comes out. Neutrophils make things yellow. Pus is exudate, whatever that word is, exudate that is rich in neutrophils. It's just a little goomba of neutrophils. And then there's dead cell debris and microbes. Then we go back to exudate and transidate. In brief, exudate is what is seen in inflammation, and transidate is what is seen in non-inflammatory states. So if somebody has congestive heart failure, or if somebody has kidney disease, they have a systemic problem as a result of their heart or their kidney disease that means that fluid is escaping from the vascular system. That is why people with congestive heart failure or people with chronic kidney disease have really swollen ankles, big swollen legs or swollen arms. That is because of their kidney disease, because of their heart disease. We will learn about that soon enough, at least the heart disease. Exudate is what we're talking about today. This is a very specific, very localized response to, let's say, tissue damage. And so fluid exudates, shall we say, or extravasates, that has a high protein content and also has lots of cells and cellular debris. Have you all learned yet about hydrostatic pressure and colloid pressure? Okay, so we won't go all about that. This is just an image of some of the things that we have talked about a minute ago. So let's go back to our steps and dive into them with a little bit more detail. So first thing that happens in the inflammatory response is vasodilation. And we already talked through why that should make sense. There's increased blood flow. There is slower blood flow. The purpose of the slower blood flow is for white blood cells, and again, neutrophils are the main players in acute inflammation, which are normally traveling through the middle of the vascular lumen at high speed, shall we say. They tend to marginate, or they just tend to find themselves at the periphery when the blood flow slows down. It's like you, when you find a traffic jam on the highway, you just find yourself drifting to the outside lanes to see how you can get around it. And this is important, and we'll talk about why in a minute. We will talk about different mediators such as histamine and how they work. All of this is regulated by certain mediators. The vasodilation, the vascular permeability. So vasodilation, which is simple enough, is, as we talked about, followed by vascular permeability, which allows in leakage of stuff that needs to leak out. Proteins and leukocytes, for example. There are a few different causes of vascular leakage. Vasoactive mediators such as histamine. Histamine causes vascular permeability and leakage. That's why type 1 hypersensitivity reactions, allergic reactions result in hives. You have localized leakage, all the stuff comes out of a vessel, and then boom, you have a hive. Damage to endothelial cells can also result in vascular permeability. And there are a variety of different causes of endothelial damage. But suffice it to say that they result in sort of shrinkage of the endothelial cells so that stuff can escape between them. Sometimes endothelial cells can even die. If any of you have ever had a sunburn, this is why you turn red when you've had a sunburn, and this is why you don't turn red as you are cooking on the beach. You turn red a couple of hours later. Because if you've sunburnt yourself, like this person has, and I found this person on Google, I have no relationship to this person. If you have sunburnt yourself the way Batman over here has, you have damaged your endothelial cells. And you've damaged them enough for some fluid and some red blood cells to extravasate. This is why sunburnt people, are they warm when you touch them? They're warm, and if you press them hard enough, which they won't let you do, it'll blanch. So that's a sunburn for you. That's just a bonus. So we've learned a little bit about transudate and exudate, and you all remember learning about hydrostatic pressure, the pressure that is caused by the pumping of the heart, and oncotic pressure, the reason why stuff that's pumped out of the capillaries at such high pressure is returned is because of the presence of albumin and other proteins in the bloodstream that draws it back. Hydrostatic pressure, the pressure that pulls or that pushes physiologically, normally, stuff out of capillaries. Now we're not talking about inflammation. It slightly exceeds oncotic pressure. But physiologically, none of us have swelling. And that's because we have something called the lymphatic system. The lymphatic system is like your little vacuum cleaner. So like the 1 or 0.1 or whatever percent it is of like excess of hydrostatic pressure to oncotic pressure, that gets vacuumed out by your lymphatic system, which performs a couple of cool functions, and we'll talk about it in due time. But in terms of a vacuum cleaning function, it'll suck up this excess fluid, and it'll travel back through the lymphatics, and it'll return to the circulatory system. I say all that to say in this lecture that in inflammation, as you can imagine, lymphatic flow is increased because you have delivery of all of this stuff into the tissues, right? So lymphatic function, the vacuum cleaner, is increased in terms of what it's trying to do. And if it's vacuum cleaning up stuff like microbes, then these little things called lymph nodes, which are scattered all throughout our body, they're these little police stations, like Cleveland has some police stations, every city has police stations. Lymph nodes are like little police stations in the lymphatic system. They recognize the antigens, and then the lymph nodes enlarge. So then you can get something called lymphadenitis. This is why you do a cervical exam when you are taught to do a head and neck exam. If someone has a bad tooth, for example, or if someone has a tonsil or abscess, It may result in cervical lymphadenopathy, enlarged cervical lymph nodes. So, following vasodilation and vascular permeability, leukocytes are recruited to sites of inflammation. The most important ones are neutrophils and macrophages. We've talked about that already. These cells are capable of something called phagocytosis. Phagocytosis refers to the ingestion and destruction of a whole lot of stuff. These cells, particularly macrophages, produce growth factors that aid in repair. We'll get to that towards the end of the lecture. You can think of them like Pac-Man. Okay, so there's a noisy, annoying picture at the bottom of this and some cramped words at the top. But I want to define a couple of words that you will come across certainly in your lectures. How are leukocytes recruited to sites of inflammation? It's a multi-step process how they get out of the inflammation and then how they are attracted to the site where they need to go to. This is controlled by adhesion molecules, which I think we'll talk about in the next slide. That's a classic boards question. And then also these molecules called chemokines. So what exactly is a chemokine? We've probably all heard the word chemokine. A chemokine is a cytokine, whatever that is, with the function of leukocyte recruitment. So it recruits leukocytes to wherever they need to go. That's why that process is known as chemotaxis, and you have something called a chemotactic gradient, as white blood cells are trying to get where they need to go. Chemokines drive chemotaxis, and chemokines create a chemotactic gradient. So chemokine is a very special kind of cytokine. What is a cytokine? A cytokine is just a messenger molecule. Cytokines are messenger molecules of the immune system. Some nerd decided to call them cytokines. Maybe you wrote Star Trek.
About which one drives this? What was the process that drives?
Chemotaxis. So chemotaxis is this process of delivering cells or attracting cells along a certain gradient so that they can come to wherever there's this highest concentration of chemokines. We'll talk about chemotactic gradient a little bit more later. Yeah, question?
So some insult happens to the organism, and chemokines bring the leukocytes. What brings the chemokines?
We'll talk about that in a minute. So chemokines are sometimes released as a result of the complement system being activated. Sometimes sometimes the chemokines themselves are components of the bacterial cell walls, things like that. So how do leukocytes get from being in the bloodstream to being, at the site of, your knee when you fell off the bike? So leukocytes, first and foremost, after the blood vessels have dilated and they've marginated out, the leukocytes first need to adhere to the endothelium. The endothelium becomes something that's called activated, and don't at the least worry about that, just they're primed and ready for whatever needs to happen. But the leukocytes first marginate, that is, they sort of align themselves near the vascular walls as opposed to traveling at high speed in the middle of the lumen. And then they roll. It's just like when an airplane lands on a tarmac. An airplane doesn't just come and stick to the tarmac. It needs to roll for a little while before it comes to a stop because it's coming in at high speed. So same thing. So leukocytes roll, and so they transiently attach and detach. It's like if you have a really bad Velcro thing and it attaches the time and you finally get it. And so this rolling is mediated by a family of proteins called selectins, which have a fairly low affinity attachment, but they slow the leukocytes sufficiently to give them an opportunity for firm adhesion, which is itself mediated by a family of proteins called integrins. This is like a favorite boards question. Rolling selectins, adhesion, integrins. I will try to, from time to time, draw some of our detailed pathological discussions into specific diseases. And we will in due course, and you all will probably also in your perio courses, learn about something called leukocyte adhesion deficiency. And so if you were to imagine that there were a disease that can arise from a deficiency in leukocytes being able to adhere. If you were to imagine that there was a disease in integrin or selectin function, and once you all learn that the mouth is full of bacteria, perhaps you've already learned that, and whenever you all learn that neutrophils and macrophages are very important for combating bacterial infections, then this disease, which is extremely obscure and you'll never see in your lives, but this disease will make plenty of sense. Leukocyte adhesion deficiency leads to increased vulnerability to bacterial infections. Oh, I can think of a bacterial infection, periodontal disease. So individuals with leukocyte adhesion deficiency are characterized by dramatic periodontal disease and early exfoliation of teeth. So all of a sudden, this goes from being an obscure disease that you're never going to see again, that you're memorizing, to really a very easy and elegant example of a physiologic process gone wrong. So that is leukocyte attachment, adhesion. Next, we're going to talk about leukocyte transmigration. There's really not much to talk about here. It's exactly what it sounds like. The leukocytes need to get through the endothelium. We have a word for that called diapedesis. Diapedesis mainly occurs in post-capillary venules. In case you're wondering what a post-capillary venule is, that's totally fine to wonder that. It's actually exactly what it sounds like. It's a venule, that is a small vein, right after capillaries. So you have your arteries, arterioles, capillaries, post-capillary venules, then you get to your venules and your veins. So we started talking a little bit about chemotaxis and how chemotaxis helps leukocytes get to where they're going following diapedesis. Chemotaxis simply refers to locomotion along a chemical gradient, hence chemotaxis. And a variety of agents can act as chemoattractants. A variety of agents can act as chemokines. Bacterial products themselves, components of the cell walls, can act as chemoattractants. That's very nice, actually, that's a chemotactic agent, because then that's not something that can ever go wrong. But other things can also act as chemoattractants as well. Various cytokines, the complement system, and arachidonic acid metabolites, whatever those are. We'll talk about those in due time. But chemotaxis, chemoattraction, is a lot like if you're upstairs and grandma's cooking and it smells nice and you sniff your way and find your way down into the kitchen. Okay, this is a picture that basically reinforces what we've talked about a couple of times. Acute inflammation happens very quickly, and acute inflammation is characterized by neutrophils. Neutrophils are your first responders, your EMS. Acute inflammation subsides within a couple of days, and with its subsiding in replacement by chronic inflammation or tissue repair, neutrophils are replaced by macrophages. So the leukocytes have gotten to where they need to be, and now they're activated, and they begin this process of phagocytosis so that they can clear up whatever the problem is. So what exactly is phagocytosis? We'll spend a few slides on phagocytosis and how cells phagocytose stuff. First, cells recognize and attach the particle that they plan on ingesting. And there's a variety of receptors for this. We're not going to talk about all of these really. Mannose is a particular sugar residue that happens to be the terminal sugar residue on most bacterial products, like bacterial glycoproteins, bacterial glycolipids. We also have glycoproteins and glycolipids, but elegantly enough, mannose is never the terminal sugar residue. It's never the last sugar on this long chain. And so if there's a receptor for glycoproteins that end in mannose, it's very specific for foreign agents. Opsonin receptors, those are receptors that are designed to identify things that have been opsonized. And we've already talked about how opsonization occurs, and I'll just point out here that opsonization greatly enhances the efficiency of phagocytosis. Another example of opsonization is putting sugar on your multivitamins. So my multivitamins have sugar on them, and I can't wait to take my multivitamins every morning. My multivitamins have been opsonized with sugar. If you go to Target, There are only, there's like a whole row of multivitamins. There's only 2 sugar-coated multivitamins for children and for men. There are gummy multivitamins and all sorts of things, but there's only 2 sugar-coated multivitamins. Question?
I may be overthinking this, but in the mouth, there are some 700 strains or so of various bacteria. I presume most of them have this mannose receptor. What is to keep the body from constantly responding to all of these? You just want them to kill the bad guys, not the normal flora, right? But how does it tell the difference?
So the way it tells the difference, it's not so much that it tells the difference, but the way or the reason why you don't have a robust inflammatory response is because this microbiome that exists in the mouth or your gut for that matter, it is separated from the circulatory system, because inflammation is only a response of vascularized tissues. It's separated from the circulatory system by an intact membrane called mucosa. And so that way, if you have bacteria which normally reside on your skin, if you have bacteria which normally reside in your mouth or in your gut, you won't get an inflammatory response. That's the basis for something called an opportunistic infection. So opportunistic infections are infections like actinomycosis. Actinomycosis is a bad bacterial infection that we'll learn about in due time. We have actinomyces. All of us have actinomyces in our mouth. If actinomycosis cannot occur, this bacterial infection cannot occur without disruption of the epithelial membrane, without disruption of the epithelial barrier. And so that's perhaps the most important reason why there's not an inflammatory response. Your question can have a more nuanced answer. You will learn about immunoglobulins, antibodies that are secreted into the saliva in due time. We will learn about superficial fungal infections, candidiasis, in due time. But in terms of a big picture overview, that's the reason why your mouth, your gut, and your skin aren't always the 5 cardinal signs of inflammation. Yeah?
Is mannose, you said something about bacterial product. Can you explain that again?
Yeah. So that's very detailed. I sort of gone to an explanation of mannose receptors just in case someone's looking at this word and means, what am I supposed to do with this word? Do I just memorize it to be on the safe side? So cellular receptors can be designed to catch mannose. And so glycoproteins and glycolipids have a whole chain of things attached to them, both sugars and protein, for example. In the example of a glycoprotein, that's why it's called glycoprotein. Bacterial glycoproteins always have as the terminal residue, the end link on the chain, is mannose. That's a feature that's unique to bacterial glycoproteins. Human glycoproteins, we also have glycoproteins. We'll learn about HbA1c. We also have glycoproteins, but our glycoproteins do not end with mannose. So if a receptor is designed to catch glycoproteins that end in mannose, it will be very specific for bacterial products. And then that can trigger an inflammatory response, or that can serve as a chemotactic agent. Does that make sense? Okay, good questions. So phagocytosis begins with recognition, and then attachment. And then there's an engulfment process. And there are words here that you don't need to memorize. If you were tasked with the responsibility of coming up with these words, I think you'd come up with the same words. The plasma membrane hinges off into something called a phagosome, which makes plenty of sense. Phagocytosis is occurring. You may guess, based on your